Before I start the definition of parallel vector field, let me just recall the last definition that we did, that was the covariant derivative of a vector field along a curve alpha. We saw that the covariant derivative of a vector field along a curve alpha, is the tangential component of this vector. You might be wondering, why are we interested in the tangential component of the vector and not simply the vector? And the answer is because the covariant derivative is a concept of intrinsic geometry. Now, what do you mean by intrinsic geometry? Does there have to be something called as extrinsic geometry? And the answer is yes. Geometry of surfaces can be broken up into two parts, intrinsic as well as extrinsic. What do you mean by intrinsic? For this, let us consider two people, Mr. A and Mr. B. Mr. A lives on, say for example, the surface. This is Mr. A, this is the surface. So Mr. A lives here, and Mr. B, you can say he is an alien. So whenever Mr. A studies the surface, his study is said to be intrinsic, and whenever Mr. B studies the surface, his study would be called as extrinsic. This would mean that whenever you move the surface from this location to another location, the properties that Mr. A studied would remain unchanged. That's one of the properties of intrinsic geometry. Now, let's see why we took the tangential component. Now, imagine this is Earth, and imagine that there is a straight road on the surface of the Earth, and Mr. A is driving a car. Mr. A is driving a car with constant speed, and hence his acceleration would be 0. But for Mr. B, looking at him from the outer space, his acceleration is directed towards the center of the Earth. We know that this is called as the centripetal acceleration, because for Mr. B, Mr. A is moving in a circular path. But for Mr. A, he is simply moving in a straight line path with a constant speed. So why is there a difference? This is a non-zero vector, and this vector is of course a zero vector. Why is there a difference? It is because Mr. A is looking at only the tangential component of this, which means that if you make a tangent at this point, since this vector alpha double dot is normal to the tangent space, we can see that it does not have any tangential component. If it were a little tilted, it would have had a tangential component, but since it is normal, it has no tangential component, and hence the acceleration of Mr. A as perceived by Mr. A is equal to 0. I think this tells us why we are interested in the tangential component of the vector and not the actual vector. Here I'm going to talk about something called as a parallel vector field. When I say parallel vector field, I am talking about the tangent vector field henceforth, okay, on a surface. So a vector field along a curve alpha on a surface S is said to be parallel at every t if I can say vector field W, yeah, if W dot, that is d by dt of W O alpha, W O alpha of t, it remains normal to the surface S at every t. Of course, what would this mean? Say for example, yeah, you have a surface and this is a curve alpha, and if I'm saying that if I'm saying that the derivative of the vector field is normal, what would it mean? I'm almost out of power. It would simply mean that it is parallel, the derivative is parallel to the normal at every point, and hence the covariant derivative of the vector field along the curve would be, by definition we saw that it is the tangential component of the covariant derivative, sorry, of the usual derivative. Since it is parallel, this W dot will be equal to some lambda times n, and hence I can write here lambda n minus lambda times n with n times n. And what would this give you? Bringing the lambda out, you will be having simply inner product of n with n, which gives you 1, and hence you have lambda n minus lambda n, which gives you 0. So basically you are saying that the covariant derivative of this vector field is equal to 0 at every point. That's the meaning of a parallel tangent vector field. Thank you. Let me go and charge my battery. Thank you. See you.